Okay, our topic for today is angular momentum. Now, a quick recap of what we know about linear momentum. Linear momentum is a vector quantity that indicates the amount of motion, and it's proportional to the speed and also to the mass. Momentum changes if there's an unbalanced force, and the product of force and time is known as the impulse, and that's the momentum change, and that's also the mass times the velocity change, v final minus v initial. And this is called the impulse. Now these are really vector relationships. Momentum has a direction that's the same as the velocity, and the momentum change has a direction that's the same as the net force. Now the main application of the momentum concept is in analyzing collisions and explosions in a closed system, because we find there that because the force is equal and opposite, the momentum change is equal and opposite, and therefore the total initial momentum equals the total final momentum, or the total amount of momentum for that system remains the same. And so here's a typical problem that you would solve in your first physics course. And you would say, okay, there's 2 times 4 is 8 units of momentum there. There's no momentum there. Afterwards, we've got 2 kilograms going at 0.5 meters per second and 3 kilograms going at some unknown speed v. And you solve for v using this momentum conservation law. So momentum was transferred from the 2 kilogram to the 3 kilogram, but none was lost in that transfer process. Okay, why do we say this? Well, because the definitions of angular momentum will follow from that. Turns out that the amount of angular momentum depends on the angular speed and on the rotational inertia. Now the units, inertia is in kilogram meters squared, and angular speed is in rads per second. When you multiply that together, you get kilogram meters squared per second. So no surprise, an angular momentum is an angular inertia times an angular speed. So some simple calculations. Let's find some angular momentum. So here's a skater spinning, and there is the axis of rotation. And the angular momentum about that axis is I omega. So the inertia is given as 50 kilogram meters squared, and the angular speed is given as 3 rads per second. So we have 150 units of angular momentum for that rotating skater. Here's the next problem. Here we have a baton that's spinning, and we're spinning it in a circle around this point right here. So this would say be a baton in a parade being spun by the twirler or whoever carries batons. Now, we want to, again, calculate the total angular momentum of the system, and that's going to depend on the inertia and the angular velocity. Now, for the inertia, there are 3 things that are spinning. First of all, there is the rod itself. Then there is the 2 masses. But we're told the rod has no mass, so it has no inertia. And the 2 masses are just point masses, so we'll calculate the inertia using mr squared multiplied by 2. So the masses are 0.25 kilos. Now, the baton is 75 centimeters long. That means it's 0.375 meters of distance from the pivot point to the mass. And so that'll give you the total inertia of the system. Now we also need the angular velocity. That's not given, but notice the linear velocity is. Well, because v is r omega, or omega r, we can find omega by taking linear speed and dividing by the distance r, and that's the distance away from the pivot point. So it's 6.5 meters per second of linear velocity for that mass, which is 0.375 meters away from the axis of rotation. So this is how you'd find the inertia and omega, and then it's trivial to calculate the angular momentum of the system. Let's try a couple more problems. Okay, so we have a bicycle wheel, and it's rotating. So angular momentum is I omega. Now the inertia in this case depends on the shape. It's a hoop, and the inertia of a hoop is mr squared. and both the mass and the radius are given, so that's how we calculate the inertia. Omega is given directly 4 radians per second, and so that's been reduced to a calculation. Next, for the Earth spinning on its axis, well, angular momentum is I omega. I for the Earth, well, the Earth is approximately or almost exactly a sphere, so the inertia will be 2/5 mr squared. Now, you would have to look on your formula page to get the mass of the Earth. It is given there. And the radius of the Earth is also given. So this would give you the inertia. Now, we have learned a trick for finding the angular velocity of the Earth. It is because the Earth rotates at constant speed and angular distance over a time. The Earth rotates 2 pi radians in 1 day, but of course a day is 86,400 seconds, and this, when you work it out, is I think 7.27 times 10 to the power minus 5 rads per second. So this is how we would find the angular momentum of the Earth. We'd multiply the 2/5 mr squared inertia by the 2 pi radians over 86,400 seconds. All right, so in each of those cases, it was pretty clear that the thing was spinning, and the angular momentum just reflects the amount of spinning motion. Well, can an object traveling in a straight line have angular momentum? I mean, at first glance, no, right? Because there's no rotation. So by itself, the answer is no, of course. But as part of a spinning system, we find that, imagine that this is, say, like a piece of wood. We're looking at it in top view, and then there's a post that anchors it to the ground. And if you, say, I don't know, throw a baseball at that piece of wood, after the baseball hits this piece of wood, it's going to spin around. So sort of thinking ahead in terms of conservation of momentum terms, we say, well, that spinning motion of the post had to come from somewhere. That angular momentum it has had to come from somewhere. It must have come from this baseball that we threw at it. So as part of a spinning system, something traveling in a straight line does have angular momentum. And it turns out that the angular momentum it has depends on this distance of closest approach, this distance r. So clearly you're not going to get any spinning motion here. It's not going to make it spin from a practical point of view, and there's no perpendicular distance, no minimum distance of approach, which is also sometimes called the impact parameter. So we expect no angular momentum here. Here we expect the angular momentum is going to be proportional to that distance r. And that's a symbol for proportionality if you've never seen it before. And indeed, we would expect that this ball going in a straight line, impacting this piece of wood, would have exactly the same effect as if this ball was spinning in a circle when we happen to whack it into the piece of wood. Because in both cases, the speed would be the same, the mass is the same, so you would expect the same sort of collision outcome. So an object going in a straight line, then, if it's going to experience a collision as part of a spinning system, does have angular momentum. Now, how much does it have? We'll do a little derivation here. Well, we've just said that the object going in a straight line, a certain distance away from the ultimate pivot point of the system, is a lot like a mass going in a circle. And for the mass going in the circle, we know that the inertia is the mass m a distance r away from the center. We'll treat it as a point mass. And we know that omega is v over r. So we could return to this first relationship, L is I omega each time, but for a point mass, which is going in a straight line, it's probably better to calculate angular momentum in this way, just because the dependence on the distance r is more explicit than it is when I write I omega. So r is the perpendicular distance from the pivot to the line of travel. It's the distance of closest approach, sometimes called the impact parameter. So we've got two relationships then. This is for point masses. And then we've got I omega which works for all masses. Let's look at some examples of some point masses. Well, here this mass is being spun in a circle. We could calculate the angular momentum using I omega, but we can just do mvr. And you see that here, this is just the natural relationship to use, because you're given the mass of 3 kilos, you're given the speed of 5 meters per second, and you're given the distance of closest approach, the closest distance to the pivot point, the 1.5 meters. So there's no doubt we could calculate I and calculate omega, but this is just a more natural way to do it. Here's another classic angular momentum problem. A planet orbiting a star in an elliptical orbit. Now, here we've got a mass of 100 million kilograms. I'm going to run out of room here. A speed of 40 kilometers a second. And then, make some more room for myself. And then a speed of 40 kilometers a second. Oh, sorry, the radius of 2 billion kilometers. So a little scientific notation challenge for you. Clearly, in prefix terms, there's a 1, a 4, and a 2, so it's going to be 8. Then there's going to be some power of 10, and the SI units are kilogram meters squared. Okay, so a little challenge then is to figure out which power of 10 this is. So it's really just a unit conversion problem. So just pause the video for a moment, and then see what you get. What's the power of 10 here? Okay, so the answer is 2 powers of 10, 6 for million. So that's 2, 8. Here's another one for 9. Kilo adds 3, that's 12. Billion is 9 more, that's 21. And kilometer adds 3 more, it's 10 to the 24. So that's the amount of angular momentum for that asteroid. Okay, so here we've got a ball going in a straight line. Now again, by itself it has no angular momentum, but it's going to hit this thing and make it spin. So as part of this spinning system, it does have angular momentum. We could calculate the inertia and the angular velocity, but these are not as readily obtainable as these 3 parameters. The mass is 0.1 kilograms. The velocity is given as 5.5 meters per second. Now, for the radius, the distance, we have to be a bit careful. Remember, it's the distance of closest approach. It's the perpendicular distance here, not this 5-meter distance. But when it gets in here, that's how the closest it ever gets to the pivot point. It's 0.45 meters. That tells us the amount of angular motion that this ball has as part of this spinning system. Okay, so that's the definition of angular momentum. So this is basically just redoing, we're doing the rotation equivalent of P is mv. Now, the impulse relationship works out the same. It basically says that angular momentum changes when there is a net unbalanced torque acting on the system. Now, really, this is just Newton's second law for rotation put together with angular kinematics. Oh yes, the last thing we could say is this is I, it's mass times the velocity change. So this is the equation for angular impulse. So as a scalar equation, it's really not particularly useful. There is one really useful and important thing we can do with it, and that's to make a simple explanation of gyroscopic motion. So this is a demonstration we'll do in class. It involves a spinning bicycle wheel, which is held by a stick running through and acting as an axle. And something really surprising happens there. And we can explain what happens using angular impulse as a vector relationship. So we'll do that together in class. But let us, at this point, just point towards the key problem that we'll work on in class after that demonstration and explanation, and that's the transfer or conservation of angular momentum. And just as was the case in Physics 11, the main reason for introducing momentum is to look at momentum transfer problems, where for a closed system, a momentum was transferred but not gained or lost. Same thing is true for angular momentum. If you've got a system that is closed, relative to external torque, so there's no net external torque on the system, then that tells us that angular momentum is conserved. The amount of angular motion at the beginning and the end will be the same. Now it can transfer between objects, but none is gained or lost in that transfer process. Now there's a bunch of ways to write that depending on which particular problem you're looking at. L might be I omega, it might be MVR, or it might be some combination of the two. And we're going to practice together writing angular momentum equations for 4 key problems. And we'll do these in class, but just to point the way, the first problem will be an elliptical orbit, where this mass starts off far away and then comes in close. This is an angular momentum conservation problem. The next one is a collision between spinning things. So we're dropping something onto a spinning thing. This is like a completely inelastic collision where 2 objects stick together and keep spinning. Here's another version of that, except the spinning thing was at rest at the beginning. Now you've got something going in a straight line that impacts the spinning thing, and then they spin together. Angular momentum is conserved in that process. And then here is the classic angular momentum conservation problem. The spinning skater, who starts off with their hands extended and then pulls their hands in at the end. And we'll see that something really interesting happens there. So we're going to do a demonstration and explanation of the gyroscopic effect, and then we'll look at these 4 key problems in class when we meet.